Hello everyone. Today we're going to start talking about the electrical distribution system and faults. So a fault occurs when you have a failure in the equipment on your electrical system, and it allows the electrical energy to flow somewhere where it shouldn't. This could be phase to phase, it could be directly phase to ground through in conductor, it could be a result of lines laying on the ground. And so an electrical fault is what happens when you get any flow of electricity through an unintended path. And this creates two significant hazards. The first of those hazards is a risk to the public, employees, and equipment, and trucks and the like for the utility. So, if there's an electrical contact, if there's live wires lying on the ground, obviously that's a significant risk. Someone could get very seriously hurt by that. The other risk that this creates, and this is one that primarily affects the assets themselves, the poles, the wires, the insulators, the transformers, and that's heat. When an electrical fault occurs, it causes a tremendous amount of energy to flow to a point that was not designed to receive that type of energy, and it's going to cause that to heat up, causes things to melt, catch fire, burn down, blow up, all kinds of bad things, but all those bad things can be traced to too much heat too fast. And so in our distribution system, electrical faults can be brought on by a whole lot of different causes. We're going to talk through some of those. And an electrical fault is always going to result in an outage to our customers. But not all outages are going to be caused by electrical faults. So let's take a look at that. In Ontario, electrical utilities are governed by the Ontario Energy Board. Also known as the OEB. These guys have a tremendous amount of influence, and you're going to see them pop up throughout the course. The Ontario Energy Board mandates that utilities report on outages spread out across 10 different categories. So let's have a look at those. First cause code we have is for an unknown outage. So this is where you have an outage, you investigate, and there's no evidence of damage. You put a new fuse in, you close the breaker back in, everything's all right, and you're never able to trace it down to a root cause. A second type of outage that you can see occurring is a scheduled outage. So if you're doing conversion work, if you have to replace a customer serving transformer, in order to do that replacement, you're going to have to take those customers out of power. So you could have a scheduled outage. The next one, loss of supply, that occurs when the utility has no power to deliver. So our assets are intact. The switches are closed. Electricity would be flowing to your home, but for some upstream cause, they don't have any electricity to deliver. Tree contacts is the first of our cause codes that's generally going to be resulting in a fault. This comes down when you get a branch or an entire tree comes crashing down into your lines, gets tangled up in it, and this is going to result in a flow of electricity either through the tree or conductor to conductor, depending how things sag when they fall. That's going to create an electrical fault that will result in an outage. And tree contacts are generally mitigated by tree trimming. Utilities run a trimming program to keep the trees well back of the lines. The standard is generally 10 feet. And as long as the trees are far enough back, they tend not to get into the lines, and you can mitigate the number of tree contacts that you have. Living here in southwestern Ontario, we have one of the highest lightning strike incidence rates in all of Canada. So we get a lot of lightning down here. And lightning is something we're going to talk about a little bit later in this course, but it results in arcing. Um, you'll get a flashover where the air insulation breaks down, and then you have an arc, and that results in a fault. So lightning is something that we can mitigate against, use it through the use of arresters, uh, but we're at a high incidence rate here in southwestern Ontario. Defective equipment is OEB speak for my stuff broke. Could be old stuff, could be new stuff, but piece of equipment that was supposed to be piece of equipment failed. Could be a pole that broke, could be an insulator that cracked, um, could be any number of things. But if the cause of the outage could be traced back to a piece of equipment that stopped doing what it was supposed to be doing, it gets categorized as defective equipment, regardless of the age of that equipment. Adverse weather. When you get a storm blowing through, you get high winds, you get that can cause your wires to sway if they're not tensioned properly. And so you can get wires slapping into each other. That will induce a fault. You get those high temperature, all the bad things that come with a fault if you get that happening. You can also get ice storms where you'll get an ice buildup, things get too heavy and overcome the structural integrity of your distribution system, and it literally falls down under the added weight of the ice. You can get heavy frosts can result if you have an excess of pollution or salt buildup from it's winter. You can get an excess of that built up, and you can get a flashover over the surface where the surface of your insulating material stops insulating. And if that happens as a result of a heavy frost, that would be categorized as adverse weather. Again, all of these things are going to result in a fault, all of these things definitely resulting in an outage. Adverse environment's one that we don't tend to see so much around here in this part of Ontario, generally due to unusual environments. So around here we'd see it if you had assets like a pad-mounted switchgear or an underground system right along a roadway that was heavily salted. All that salt starts working its way into the equipment and causes corrosion, and that corrosion results in a failure or tracking across the surface because salt water is incredibly conductive of electricity, and then you get an insulation breakdown and off she goes. You can also get similar effects if you end up with an excess of pollution. Some types of pollution and ash can end up being fairly electrically conductive, and if you get enough of it on the surface of your stuff, it can cause tracking and an electrical conducting to begin occurring over the surface of your insulators, resulting in a fault. Human element is the OEB speak for distribution staff messed up. Somebody opened or closed a switch they should not have, and that resulted in an unintended outage for the customers. Or someone was working on a piece of equipment and did something they should not have done and broke it, and that resulted in an outage for the customer. Foreign interference is OEB code for everybody else broke my stuff. So here you have motor vehicle accidents and reckless people with backhoes digging in and destroying your underground plant, and thieves chopping your plant down because they want to steal the copper off of it. Malicious folks intentionally breaking stuff, kites getting into your wires and causing an arc and a fault and the power going out. So all those things that get imposed upon your distribution system that aren't your fault fall under that category. And the last cause code that the OEB has us working on or categorizing is what they call a major event. So this could be your 100-year storm, or if you're living closer to the coast or down south, this could be a major hurricane event or an ice storm. This is something that causes a tornado, something that causes widespread devastation, far and away above the usual levels of damage you would see for that kind of season. And the OEB allows you to exclude that when you're trying to figure out your reliability stats because it's considered something that's so unusual. So these are all the causes, the categorizations that are used when we're looking at causes of outages. And some of these are going to be fault inducing. So typically your fault inducing ones would be trees, lightning, defective equipment, foreign interference, major events. These would all be cause a fault. And then scheduled outages, loss of supply, human element are usually resulting in an outage, so no electricity to the customer, but often don't involve an actual failure and a high current, high energy event to occur. Unknown causes, hard to say. That could go either way because we don't know. It's a definitions problem. So, talked about some of the things that can cause a fault. Talked about that a fault is an unusual flow of electricity. So, what does that look like? What does that mean? Let's go have a look at what we did in our lecture last week. Last week we looked at this sample circuit and we ran our calculations on it and we found that at the source we were seeing about just under 24 amps of current flowing. A fine number. Typically a distribution circuit would be built to withstand maybe 600 amps maximum at the source. Sustained would be considered normal. Number more like 300 to 400, typical comfortable maximum operating value, much like your car. You can run it up at the red line, but not recommended for longevity. That said, if the red line's at 6 or 7,000 RPM, getting your tachometer up around 3,000 RPM when you're passing somebody or cruising down the highway certainly doesn't represent a risk of increased wear on your vehicle. That's just normal operating. So for our feeders, we typically see 600 amps would be considered the equipment limits. It's like the red line on your car. And a typical operating value would be about half that. So we took a look at our example from last week and we saw that we were sitting at about 24 amps. That's quite lightly loaded. And as a result of that, when you get out to the end of our circuit out here, this guy's got almost no voltage drop at all across the length of the line. So he's still getting really nice quality power delivered to the premise. So things are good. Now, this week, let's take a look at what happens when things go bad. So we're going to start out with, here, let's take a tree. We have a beautiful tree, and the tree falls down right here, falls right into our power line with the transformer attached to it, and the wires get tangled up into the tree. What this is going to have the impact of is it's going to result in a new path for the electricity to flow in, right here. So let's take a look and redo our circuit analysis. Instead of starting out with the 200 and the 0.378 ohm sources in series, we start out with a short circuit of 0 ohms in parallel with our transformer rated for 200 ohms. Oops. So here we get into a little piece of bad math. That doesn't deserve to be green. 1 over 0. This is, strictly speaking, undefined. However, we can come up with an approximation of what this does. So if we take a look at this, we can see that 1 over 0, so 1 over 1, that's 1, easy enough. 1 over 10 is 1/10. 1 over 1,000, the number's getting smaller. If we go the other way, we see that the number starts getting bigger. As that denominator goes down and approaches 0, the combination goes up. And so we get this case where 1 over 0 approaches infinity. So we're looking at 1/200th plus approximately infinity, which is infinity. So our R total goes to 1 over infinity, which is 0. Anytime you end up with a fault, 0 ohms, anytime you end up with 0 ohms in parallel with something, it always goes to 0. So the only impedance we have left here is our 0.378. So this leaves us with another parallel calculation. So over here we end up with 0 in series with 0.378, which just gives us 0.378. 0.378 in parallel with 200. As you can imagine, this is going to be pretty close to 0.378. Once we do that parallel, we find the bar really does not move very far. So we can redraw our circuit. So our R equivalent for the entire circuit, series value for these two numbers, so now we can take that forward and take a look at our total current. Now we're going to make the assumption here. Now we're going to assume idealized sources for now, and we're going to be neglecting a couple other complicating factors because they don't really help prove the point of what's occurring here. So this is an approximation of what's going to occur in practice. see all of a sudden flowing through our lines, we've moved from 24 amps all the way up to 4,700 amps and change, almost 4,800 amps. We also see that in practice, our two load transformers don't really contribute at all. The only contributing factor is the resistance of the line itself. Had this fault occurred closer in, you can imagine had the fault occurred at the first transformer instead of the second, we wouldn't have this 0.37 here. We'd see almost 4 times the amount of current flowing. So these faults result in incredibly high amounts of current flowing, far in excess of what the equipment is rated for. Remember, the equipment is rated for maybe 600 amps if it's a full-scale feeder. And so this sort of a current flow is going to be delivering a lot of excess heat. It's going to be delivering a ton of energy into that fault point. It's going to be causing some significant damage, not just at the fault, but it's going to be overheating all the assets all the way back to the station and putting additional stress on those as well. So we're going to pick up on that thought in the next set of videos.